This is a recast of the 6,300-word piece, Energy-Based Models, EBMs, from chnepat.com. This article discusses the concept of energy-based models, EBMs, in machine learning, highlighting their ability to capture complex patterns and dependencies in data. It emphasizes the importance of studying EBMs for understanding energy usage patterns, shaping policy decisions, and directing investments in renewable energy sources. The article also mentions various applications of EBMs in computer vision, natural language processing, image and video processing, and other domains. It discusses the principles, components, training procedures, and optimization techniques of EBMs, as well as their advantages, challenges, and potential for future advancements. Let's listen in.
So the article talks about a new approach in machine learning called energy-based models, or EBMs. These models are gaining interest because they can capture complex patterns and dependencies in data, which traditional approaches struggle with.
That's right. Traditional generative models use explicit probability distributions, but they often struggle to capture the intricate relationships present in real-world datasets. But EBMs are different. They define a scalar energy function that assigns higher energies to implausible configurations and lower energies to plausible ones.
And by learning this energy function, EBMs can capture the underlying structure of the data. This makes them attractive for various applications in machine learning and computer vision.
Exactly. EBMs are a type of probabilistic model widely used in machine learning and computer vision. They focus on the energy function, which assigns a scalar value to every possible data configuration. This energy function represents the compatibility between the data and the labels, with low energy indicating a good match.
And training an EBM involves minimizing the energy function over the training set. This means that the model assigns low energy values to the correct labels. By considering the energy function, EBMs can capture complex dependencies and perform well on tasks such as image denoising and object recognition.
That's right. Now let's talk about why studying EBMs is important. Firstly, EBMs provide a valuable tool for analyzing and predicting energy usage patterns within a specific system or industry. By studying these models, researchers can identify opportunities for energy efficiency improvements and develop strategies to reduce energy consumption.
And not only that, EBMs also play a significant role in shaping policy decisions and directing investments in renewable energy sources. The insights gained from studying EBMs can inform policymakers about the potential impact of different energy policies on the environment and economy.
Absolutely. By studying EBMs, we can work towards a more sustainable future by optimizing energy usage and reducing our reliance on fossil fuels.
Now let's talk about why EBMs have gained popularity in machine learning. One reason is their ability to model complex distributions. Unlike traditional models that use explicit probability distributions, EBMs focus on capturing the energy landscape of the data.
That's right. This energy landscape is defined by a function that assigns a scalar value to each configuration of the data. By minimizing this energy function, EBMs can identify the most probable configurations.
And another advantage of EBMs is their ability to incorporate both observed and unobserved variables. This makes them versatile for modeling a wide range of data types. They have been successfully applied in various fields, such as image and speech recognition, natural language processing, and drug discovery.
That's true. EBMs are flexible models that can capture complex dependencies between variables. They define an energy function over the training data, and the goal is to find the parameters that minimize this energy function.
And one advantage of EBMs is that they can easily incorporate prior knowledge or constraints by adding terms to the energy function. This allows researchers to shape the model based on their specific requirements.
Additionally, EBMs have the flexibility to handle missing or corrupted data. They do this by assigning higher energy values to inconsistent states, which makes them robust in real-world scenarios.
Absolutely. And because of these advantages, EBMs have been successfully applied in various domains like image classification, natural language processing, and speech recognition.
And let's not forget that EBMs can also generate new samples by sampling from the energy function. This is especially useful in tasks such as image generation and data augmentation.
So in summary, EBMs are a promising alternative to traditional generative models. They can capture complex patterns and dependencies in data by defining a scalar energy function. This makes them attractive for various applications in machine learning and computer vision.
And studying EBMs is important for understanding energy usage patterns, shaping policy decisions, and directing investments in renewable energy sources. EBMs also offer the advantage of being able to model complex distributions and handle missing or corrupted data.
Absolutely, EBMs have come a long way in their history and development. Initially introduced as an alternative to traditional probabilistic models, EBMs gained popularity due to their ability to handle complex data distributions and learn high-dimensional representations. One key milestone in their history was the introduction of restricted Boltzmann machines, RBMs, which emerged as a powerful and efficient learning algorithm.
That's right. RBMs opened up new possibilities for EBMs and paved the way for further improvements. This led to the development of deep belief networks, DBNs, and deep Boltzmann machines, DBMs, which are more advanced versions of EBMs. These advancements have made EBMs an integral tool in various applications, such as natural language processing, image recognition, and generative modeling.
When comparing EBMs with other machine learning models, we see several notable differences. Unlike generative models like RBMs and variational autoencoders, VAEs, EBMs do not explicitly model the data generation process. Instead, they focus on capturing the underlying energy function that determines the compatibility between inputs and outputs.
And another difference is that EBMs can handle both unsupervised and supervised learning tasks, unlike discriminative models like support vector machines, SVMs, that exclusively deal with supervised learning. Additionally, EBMs offer a more probabilistic framework than maximum margin classifiers and deep neural networks, making them ideal for modeling complex and multimodal data distributions.
Absolutely. Moving on, let's talk about the principles and components of EBMs. These models are built upon the fundamental principles of energy conservation and the minimization of energy. The main idea behind EBMs is that a system's behavior can be explained by a global energy function, which assigns an energy value to each possible configuration of the system. The components of an EBM include variables that represent the system's state and parameters that describe the interactions and constraints within the system.
That's right. By optimizing the energy function, EBMs can predict the behavior and dynamics of various systems, providing insights into their underlying mechanisms. The energy function plays a crucial role in EBMs as it defines the relationship between the input data and the model's learned parameters. It acts as a measure of the compatibility between the input data and the model parameters, indicating how well the model can reconstruct or generate the input data.
Exactly. The energy function is designed to minimize the energy when the input data matches the model's ideal state. By iteratively adjusting the model parameters to reduce the energy, EBMs can learn meaningful representations of the input data. So, it's a fundamental component in understanding and training EBMs.
Now let's talk about the training procedure and optimization techniques for EBMs. The training procedure typically involves maximizing a tractable lower bound on the log likelihood of the training data. This is estimated using a form of contrastive divergence or Markov chain Monte Carlo, MCMC sampling.
However, training EBMs using MCMC can be computationally expensive and time-consuming. To address this, various optimization techniques have been proposed. For example, persistent contrastive divergence and parallel tempering improve the efficiency and convergence of the training procedure.
That's right. There are also approaches like score matching and noise contrastive estimation that simplify the training process and provide better training objectives. These techniques enable the effective training and optimization of EBMs, enhancing their performance in modeling complex and high-dimensional data.
And despite their success, EBMs do face challenges, such as the computational complexity of energy inference and the need for large amounts of training data. However, ongoing research efforts are continuously improving the practicality and scalability of these models, making them a promising avenue for future scientific advancements.
Absolutely. It's an exciting time for EBMs, and we can expect to see even more advancements and applications in the coming years.
Definitely. One area where EBMs have found significant application is in computer vision tasks, such as image classification and object detection. By capturing the energy distribution of images, EBMs can accurately differentiate between different classes and locate specific objects within an image.
That's right. EBMs have the ability to model complex dependencies, handle missing data, and incorporate prior knowledge into the modeling process. This makes them a powerful tool for analyzing and understanding complex systems in various domains.
Absolutely. And it's not just computer vision where EBMs excel. They have also shown remarkable performance in natural language processing tasks, including language generation and machine translation.
That's true. Through the energy landscape of textual data, EBMs can capture semantic relations and produce coherent and meaningful outputs. This has opened up new possibilities in language processing and generation.
Definitely. The applications of EBMs extend beyond computer vision and natural language processing. They are valuable tools in numerous fields that require modeling and analysis of complex data sets.
Absolutely. One field where EBMs have made significant contributions is image and video processing. This plays a crucial role in various applications, including computer vision, multimedia systems, and medical imaging.
Image and video processing techniques allow us to enhance image quality, remove noise, analyze and extract relevant features, and even enable machines to understand visual information.
And when it comes to EBMs, image and video processing provides valuable insights into generating accurate and realistic visual representations. By utilizing EBMs, we can capture and model the intricate details of images and videos, leading to advancements in object recognition, tracking, and even computer-generated imagery.
That's right. And one specific application of EBMs in image and video processing is image denoising and inpainting.
Image denoising involves removing noise from an image, while inpainting involves filling in missing or corrupted parts of an image.
And EBMs have emerged as a powerful approach for tackling these challenges. By formulating denoising and inpainting as energy minimization tasks, EBMs aim to find the image that best fits the observed data while satisfying certain constraints.
That's correct. Deep neural networks are trained to effectively model the underlying image distribution and estimate the missing information. And the use of EBMs in image denoising and inpainting has shown promising results, demonstrating the potential of this approach in various real-world applications.
Absolutely. Another important application of EBMs is in object recognition and segmentation in computer vision.
Object recognition and segmentation are fundamental tasks in computer vision, and EBMs have shown promising results in these areas.
Right. EBMs capture the dependencies between the observed data and the hidden structures through an energy function.
By minimizing this energy function, EBMs can effectively model the complex relationships between different image regions and objects. This allows them to perform accurate object recognition by identifying the presence and location of objects within an image.
And not only that, EBMs can also address the challenging task of image segmentation by partitioning an image into coherent regions based on their visual characteristics.
That's true. Through their ability to capture complex dependencies, EBMs offer a powerful approach for object recognition and segmentation in computer vision.
And that wraps up our discussion on the main points of the article. Do you have any final thoughts, Ben?
I think it's clear that energy-based models have tremendous potential in various domains, from computer vision to natural language processing. Ongoing research and advancements in this field will surely lead to even more exciting applications and developments in the future.
Absolutely. Thanks for tuning in, everyone. In the article, it mentions that motion tracking and video analysis using EBMs is a rapidly growing field in computer vision and image processing. By utilizing energy-based models, researchers can accurately track and analyze the movement and behavior of objects within video sequences. This technology has a wide range of applications, including surveillance systems, sports analysis, and virtual reality.
That's right. The energy-based models utilize an optimization process to estimate the parameters of the motion model by minimizing an energy function. This allows for the reconstruction of object trajectories, identification of anomalous events, and extraction of meaningful features from video data. As motion tracking and video analysis using EBMs continues to advance, it holds great potential for enhancing various fields and industries.
Moving on to natural language processing, NLP, it plays a crucial role in a wide range of applications, such as information extraction, sentiment analysis, and machine translation. NLP enables machines to understand, interpret, and generate natural language, facilitating communication between humans and computers.
Yes, and energy-based models have proven to be effective in various NLP tasks because they can learn complex patterns and capture dependencies between words. By modeling the interactions between the constituent parts of a sentence, EBMs can effectively represent the semantics and syntax of natural language. This provides a powerful framework for improving the accuracy and performance of NLP systems.
Absolutely. EBMs have proven to be effective in language generation and sentiment analysis tasks. In language generation, EBMs generate coherent and contextually relevant sentences by modeling the energy landscape of different word combinations. They capture the syntactic and semantic relationships between words, resulting in high-quality generated text.
And when it comes to sentiment analysis, EBMs excel at quantifying sentiment using an energy function. They assign positive or negative sentiment scores to text input, allowing for accurate sentiment classification. This is crucial for various applications, including social media monitoring and customer feedback analysis.
Moving on to text classification and summarization, EBMs can also be applied in these areas. Text classification involves automatically categorizing or tagging text documents based on their content. EBMs can create models that assign labels or categories to text based on the energy levels associated with a given label.
And in text summarization, EBMs can identify the most important information within a text by assigning lower energies to less relevant information. By employing EBMs, text classification and summarization algorithms can effectively analyze and process textual data.
Anomaly detection and fault diagnosis are crucial in various systems, and EBMs can be utilized for these purposes as well. By comparing the energy levels of different states of the system, anomalies or faults can be identified when the energy values deviate significantly from the expected range.
That's right. EBMs provide a holistic approach to anomaly detection and fault diagnosis, enabling the detection of both known and unknown anomalies. Additionally, by localizing the abnormalities within the system, EBMs facilitate targeted diagnosis and efficient troubleshooting, improving the overall performance and reliability of the system.
Another interesting application of EBMs is in identifying abnormal patterns in data. By assigning higher energy to abnormal patterns and lower energy to normal ones, EBMs can effectively distinguish between them. This makes them a valuable tool in domains like fraud detection, health monitoring, and network security.
Absolutely. With their ability to capture complex relationships, EBMs offer an efficient solution for detecting abnormal patterns in data. They leverage the concept of energy functions to capture the interactions and dependencies between input variables and target variables.
And finally, in complex systems where fault detection and diagnosis are crucial, EBMs have gained significant attention. These mathematical models can effectively detect and diagnose faults by modeling the energy flow and considering the system's dynamics. They can also provide insights into the root causes of faults, enabling proactive maintenance and preventing unexpected failures.
Definitely. EBMs present a promising avenue for future research in generative modeling as well. They offer a unique perspective by focusing on energy functions rather than probability distributions. By learning an energy function that captures the underlying structure of the data, EBMs can generate highly realistic samples.
That's right. And one of the key advantages of EBMs is their flexibility and adaptability to different types of data. Unlike traditional machine learning models that require specifying a probability distribution, EBMs learn the energy function directly. This allows them to better capture the dependencies and interactions in the data.
Absolutely. And this flexibility extends to the types of data that EBMs can handle. They can accommodate various forms of input such as images, text, or numerical data. So whether you're working with computer vision, natural language processing, or recommender systems, EBMs can be applied in diverse domains.
They can even handle both structured and unstructured data, as well as handle missing or incomplete data. This makes EBMs an excellent choice for analyzing and modeling real-world datasets that often exhibit a high degree of variability and heterogeneity.
And speaking of handling complex datasets, EBMs have become invaluable tools in dealing with high-dimensional and complex data. With their ability to effectively handle datasets with numerous features and variables, EBMs provide a robust framework for analyzing intricate patterns and relationships.
Right. And by incorporating energy functions, EBMs assign a scalar value to each data point, representing its degree of compatibility with the model. This allows the model to capture complex interactions and dependencies within the data, leading to accurate prediction and decision-making.
However, it's important to note that there are challenges and limitations when it comes to using EBMs. One major challenge is the computational cost. Because EBMs require intensive computations to estimate the energy function, training and evaluating them can be time-consuming and resource-intensive.
Absolutely. And another challenge is the high-dimensional nature of the problem. Learning parameters in EBMs can be challenging due to the vast number of dimensions involved. This is something that researchers are actively working on to improve.
Definitely. And while EBMs offer interpretable models, understanding the internal workings and decision-making processes of these models can still be difficult. This is an area that requires further research to enhance the interpretability of EBMs.
And let's not forget the challenge of data availability. The learning process of EBMs heavily relies on having a large amount of labeled training data. This can be a limiting factor for applications with limited data availability.
That's true. And lastly, the difficulty of training and optimizing large models is another challenge. As EBMs grow in size and complexity, traditional optimization techniques can become computationally expensive and time-consuming. Advanced optimization algorithms, regularization techniques, and parallel computing strategies are needed to address this challenge.
So, while there are challenges to using EBMs, their advantages make them a promising approach for tackling complex machine learning tasks. They offer flexibility, adaptability to different types of data, and the ability to handle high-dimensional and complex datasets.
Definitely. And despite the challenges, EBMs have already proven their worth in various domains such as natural language processing, computer vision, and bioinformatics.
Absolutely. One key advantage of EBMs is their ability to capture complex relationships and make accurate predictions. They do this by assigning energy scores to different inputs, where lower energy values indicate more desirable states. This allows EBMs to represent complex and high-dimensional data effectively, making them particularly useful for tasks like image and speech recognition.
That's right. And unlike other models that use probability distributions, EBMs learn a more flexible energy landscape, which allows for greater expressiveness and capturing intricate patterns in the data. This flexibility is what sets EBMs apart and makes them so effective in handling complex tasks.
However, one major challenge with EBMs is the calculation of the partition function, which is necessary for obtaining the model's prediction probabilities. Various techniques, such as Monte Carlo methods and mean field approximations, have been proposed to address this issue. These techniques aim to improve the efficiency of training EBMs and enhance their convergence and learning rates.
Absolutely. And advancements in architectures and algorithms for EBMs have been a topic of great interest in recent years. Researchers have developed deep architectures for EBMs that utilize multiple layers of hidden units to capture complex relationships in the data. These deep architectures have shown superior performance in tasks like image and speech recognition.
That's true. And there have also been advancements in learning algorithms for EBMs, such as contrastive divergence and persistent contrastive divergence. These algorithms effectively address the training challenges of EBMs and pave the way for more efficient and accurate energy-based modeling. This enables further applications of EBMs in various domains.
Ethical considerations and fairness are also crucial when using EBMs. It's important to ensure that these models do not reinforce existing biases or create new forms of discrimination. Clear guidelines need to be established to prevent any potential harm caused by their misuse. Transparency and accountability should be essential principles in the utilization of EBMs to ensure their ethical and fair application in various domains.
Absolutely. And another interesting avenue of research is the integration of EBMs with other machine learning techniques. Combining EBMs with deep learning methods has shown promising results in tasks like image classification and natural language processing. This integration allows researchers to leverage the strengths of both models and create more robust and efficient learning algorithms.
That's right. And the fusion of EBMs with reinforcement learning has also gained traction, offering opportunities for learning policies in complex environments. This integration opens up further possibilities for enhancing the performance of EBMs and extending their applications in various domains.
Definitely. Another important point to note is that EBMs do not explicitly model the probability distribution of the training data, unlike other generative models like GANs or VAEs. Instead, they define an energy function that quantifies the compatibility between an input and the trained data. The goal is to minimize the energy for samples drawn from the training data and increase the energy for samples drawn from a noise distribution.
Right. And this flexible framework allows EBMs to accommodate various data types and generate samples with controllable properties. This means that EBMs can be used to model complex systems and capture intricate relationships within the data, making them a powerful tool in machine learning research.
Absolutely. In conclusion, while there are challenges to using EBMs, their advantages make them a promising approach for tackling complex machine learning tasks. They offer flexibility, adaptability to different types of data, and the ability to handle high-dimensional and complex datasets. Ongoing research and advancements in EBMs have the potential to further improve their capabilities and efficiency, opening up new opportunities for their utilization in various domains.